All right. Sorry. So I saw that the lecture was kind of titled Introduction to Basic Learning Theory. I'm going to do my take on it. Okay. So we've had a lot of kind of the AI boom and a lot of things happening, and I really kind of wanted to at least start the talk with going like really retro, kind of going back to kind of results from early 60s, and then let's see how far we get along. And I wanted to start with sequence prediction because A, it's my favorite topic. Kind of, in the past, I've done a lot of online learning, and it's kind of one of my favorite topics. And B, it's also very timely in terms of kind of what's happening right now. Right? If you look at kind of the AI revolution, there's like a whole bunch of there's a whole market out there for LLMs and what they can do. And if you actually look behind the curtain, kind of like the main workhorse unarguably is basically the next token prediction. So given a bunch of tokens, can we predict the next token? And then of course, there are a lot of bells and whistles and all kinds of things that kind of really push the performance out there. We had our friends talk about RL, and RLHF is kind of one of the takes on RL that's kind of used for tuning all of these guys. And there's like a whole bunch of other bells and whistles. But I wanted to kind of start with just next token prediction. It has various names: auto regression, online learning, sequential prediction, et cetera, et cetera. And I wanted to take it back to probably the simplest setting out here. Okay, let's start there and then see how far we go. So the simplest setting is that of bit prediction. So there is this bit or this kind of coin prediction or bit prediction game. It's even simpler than rock, paper, scissors. But I really like this game in terms of analysis, in terms of kind of understanding the math behind it, because it already gives us glimpses of how we should develop algorithms and kind of what's the geometry kind of underlying such, prediction problems. Okay, so the game is the following. You have two players, and each of them, so there's player one and player two. Player one basically first chooses a coin. It's either heads or tails, but that coin is not revealed to you. Right? So I've kind of closed the head, the face of the coin. And then now player two is going to pick another coin. And now what's going to happen is they're going to match. And so if both of the coins had either heads or tails, so if we get a match, then both the coins go to player two. And if not, it goes to player one. Right? So it's a simple game. I'm just trying to predict kind of what your next bit is going to be. And here's a question for you guys. And again, feel free to interrupt me at any time. I really want this talk to be interactive. So what is the optimal strategy for this game? Right? If this was the game, two players are playing, and what's the optimal strategy for either one of the players? Right. So the obvious answer is we're going to flip a coin, and with 50% chance it's going to be head, with 50% chance it's going to be tails. Right? And that's where the game should end, right? Like, irrespective of how many times I do this, I can essentially kind of just flip a coin, and that's the min-max optimal strategy. But that's not where the story stopped, and this is not where it stopped even way back, kind of, I said retro, I'm going to take it back to the days of kind of the Bell Lab glory days. This is back in, I think, around the 50s, 60s. I forget the exact date. Sorry about that. I will look it up and let you guys know. But this is David Hagelberger. I'm pretty sure I'm butchering the name. Sorry about that. So he basically wanted to kind of see whether he could play this game against humans and win. And what we do know is humans are notoriously bad at coming up with random coin flips. Right? If you actually, and this is something that in basic probability theory courses, faculty kind of tend to do this, where you kind of ask students to write down long sequences of guesses or basically of random coin flips, like ones and zeros. And you can pretty much pick out kind of which ones are written by the humans, because humans are bad at coming up with random guesses or with random coin flips. And so he basically wanted to make a machine that could predict what the humans did. And he was really successful in that he was able to come up with a machine that could beat random chance by a fair enough margin. So I think if I ask you, for instance, give me a sequence of random numbers, the simplest form of mistakes that people do is they kind of conflate having kind of drawing from the uniform distribution from saying that I require kind of equal number of ones and zeros, right? And they tend to do that even in smaller and smaller packets. So it's actually like fairly easy to kind of figure it out. Not quite. So he wanted to make, so originally he made like this was the time when finite state automata was like a big thing, and he wanted to build like a finite state automaton machine that could beat the humans. And it was handcrafted, so it was not like specific, so it was not specifically designed to kind of, I don't know how much of statistics was used, because it was more like a pet project within Bell Labs. And so that's what he did out there. I think this is, at least from what I have from the internet sources, this is supposed to be the machine that he created. And then kind of this got Claude Shannon interested. He came in and he kind of wanted to make another machine that did better than David's machine. And this was the machine that he created, right? So essentially you have like either heads or tails. You can switch the switch left or right. And I suppose a light glows if you're right. And so these two guys, they had their machine and they were able to beat humans by a good margin. And of course, what they were more interested in is to see kind of amongst, if they played their machines off each other, which one would win. Okay, so that's kind of the setup that I want to look at. And let's see if we can formalize this problem, right? This is a simple prediction problem. And I'm going to formalize it as such. So we're going to think of it. So for the purposes of at least today, we're going to fix the number of rounds for which we are going to play. It's some n. Think of it as some large number, but that's some number that I'm going to say is fixed. Later on, if time permit, I can tell you strategies to kind of adapt to this n. Okay, and what the learner is going to do is the learner is going to, in a possibly randomized way, the learner is going to pick some y hat t. So think of the learner as player 2. Player 2 is going to randomly pick a y hat t, and this randomness is not revealed to the other player, right? So you can think about the player as actually picking the probability of heads or tails, and then the actual coin flip is not known to the other player. Then the true outcome yt, which is chosen by player 1, is revealed to us. And then the learner suffers the loss, which is if the guess is correct, they get a 0 loss, otherwise they get a loss of 1. Right? This is kind of what we are interested in. And let's start with the simplest goal, and this goal is already good enough to at least ensure that we're not losing too badly. Okay, the goal is, so for those of you who are familiar, and given that you've seen the lectures, that you've attended like a few lectures before, I'm sure this term may have been used before. It's just called regret, which is basically saying what's my cumulative loss? That's how many coins did I earn, minus the loss of the best model. And here I'm going to take a very simple notion of the best model. So let's say I played for n number of days, and then after this fact, after the n number of days, what happened in those n days are revealed, I'm going to pick the majority, right? So if most of the days it was heads, if more number of days had heads than tails, I'm going to say heads, otherwise tails, right? So that's the majority in hindsight, and what we want to do is make sure that this quantity is small, okay? So here's a question. So if I had the optimal policy, what's an upper bound on this that I can guarantee against any adversary? Right? In fact, let's start with this. If I had the optimal policy and I played against the min-max optimal policy, that is, if the opponent is flipping coins, okay? So the YTs are generated by coin flips, and I am allowed to run any algorithm out here. What's the best I could do in terms of regret? How large would it be? Sorry, yeah. N by 2, I'm looking at the difference, right? So this is what's my loss, right? So my loss is going to be, as you guessed it, kind of n by 2, but then I'm also subtracting away the loss of majority, right? Any other guesses? So it's got to do with how much off we are in terms of deviation, right? We are flipping n coins, and n over 2. So as our friend pointed out, y hat t really cannot predict random coin bits, right? In fact, no algorithm can predict. So this guy is just going to be a constant half. So this quantity here is n over 2, but then you're only comparing yourself with majority, right? And what we expect from a random coin flip is that its expected value should be essentially a half, but you always have some deviation around a half, right? It's roughly between minus square root n over 2 and plus square root n over 2. And so the best bound that any algorithm could kind of guarantee for this guy here is roughly of the order of square root n over 2, right? And here I'm just saying, let's try to do this when the opponent is just flipping coins. Now, the interesting question that we are going to ask is, what can we do when the opponent is not flipping coins? When there is some strategy to the opponent, what's the best we can get as an upper bound here? Okay. And the interesting part is the answer is still going to be basically this square root n over 2 is still possible. Okay. And this is a result that was, it was not shown in exactly this form, but it was basically shown back in 65 by Thomas Cover. And I'll start with that because it kind of gives us a way as to how you can think about designing the algorithm. In this case, because it's a simple enough problem, you can kind of solve it end to end. And it also gives us a notion of the geometry, as I mentioned. Okay. All right. So what I was asking was, what is the strategy, right? So here I want to take a couple of minutes to see if I can solicit some strategies to kind of show you that while the problem is interesting, it's also not trivial, right? So feel free to kind of chime in with any policies, right, or any strategy or policy. If you were kind of trying to predict the next bit, and let's say that I get to see, let's say I'm at day t, and I get to see the previous t minus 1 coin flips, right? Like I get to see whether the opponent played heads or tails and so on. Now, what would be, how would you kind of, what would be your strategy design, or what would you want to do? Yeah. Perfect. So the answer was, let's take, if for instance in the past over the t rounds, let's say 70% of the time the opponent played heads, then I'm going to predict a head, right? I'm going to predict head with probability 0.7. Okay, any other? Yep. Right. So I guess here we are trying to kind of guess what the opponent is doing. And so our friend basically gives the answer that maybe we want to try to flip because humans want to kind of get it towards 50%, right? Again, so there might be some strategies that would selectively work against humans. Again, I'm not sure whether that strategy specifically would work, but there are strategies that would work against humans. But here we want to kind of even be able to get a safety kind of guarantee or rail even when we are playing against, say, Shannon's machine or David Hagelberger's machine, right? So, okay, so let's go with, I kind of had two guesses in the next slide. Let's go with, and one of them matches what our friend mentioned, which is playing the probability of head so far or tail so far, right? So let's go with that. Yeah, go for it. Um,
Best algorithm means that if I'm doing something deterministic, for instance, if my prediction is, I look at the decimal expansion of pi, and if it's odd, I put 0, if it's even, I put 1. Then the best algorithm gets everything right because you know that you're drawing something from pi. So is that how you compute the regret? Like the best algorithm then has a loss of 0.
No, so again, here what we are saying is, so we'll say that an algorithm has a guarantee if it has a guarantee against every single adversary or every single, like, so let's say you and me are playing, right? So I have an algorithm. Now, if you deterministically, let's say you're going to play based off of like the binary expansion of pi, and if I knew this, then yes, my loss is going to be 0, right? But the thing is, I don't know what you're going to play, and I want a guarantee that holds for everything that you could possibly do, right? And again, as I kind of state this, it should become clear that such a guarantee in general kind of, so that's why this definition of regret that I mentioned becomes important, because if I didn't have this comparator here, and if I just said, I want to minimize this, right? There is no way you can get things right, especially if you have a deterministic strategy. Because my strategy is always just going to be to say the opposite of whatever you're saying, at least the way I've written down the game. Right? So one thing that becomes clear from this is already that you need a randomized strategy. And as long as, if you don't have access to like a random number generator, or if your random number generator is compromised to your opponent, then you're going to lose the game. Right? But if you did have access to the random number generator, what's the best I could do against any adversary out there? Okay, that's the setup.
Yes, I would just change my target. You're comparing me to the best single plus 1 Whoever's doing better.
Right. So the other strategy that was proposed was basically look at whether there are more heads now or more tails now, because that's what the benchmark does, and choose that at every step, right? That's not going to work. Why is that? Because imagine that I were the adversary and you were doing this with me, right? What I'm going to do is, now let's say the number of heads is one more than the number of tails. Then I know that you're going to play heads, so I'm going to choose tails, right? So I can always, so any deterministic strategy, not just this strategy, any deterministic strategy. Huh?
At every step I will do.
Yeah, every step you'll lose, right? So this guy will still be like n over 2, but this guy is going to be of order n. So you're going to have a bad regret that's linear in n. So kind of the goal for us is to make sure that this regret here is small O of n. So it shouldn't grow linearly in n. Okay, that's what we are asking, whether it's possible or not. So as I mentioned, so the majority, or in fact any deterministic algorithm is going to fail at this problem, because clearly I can always kind of look at what you're doing. The strategy that requires a little bit more thought is what our friend mentioned, which is a like a randomized strategy where the probability with which I'm going to give you heads is going to be the fraction of times heads occurred in the past, right? But my claim here is that that's also not going to work, okay? Why is that? Imagine we had n rounds, right? What I'm going to do is the following. And again, this might seem funny to some of you guys. As computer scientists, we are taught to work in zeros and ones. As learning theorists, we prefer to work in minus ones and ones. So -1 is tails, +1 is heads. Okay. So imagine I did the following strategy up to n over 3 rounds. Let's say that n is divisible by 3 for this purposes. So up to n over 3 rounds, I'm going to keep on playing tails. Okay. And then I switch and keep on playing ones. Okay. That's the strategy. And I claim that the strategy that you mentioned is not going to work here. And the reason for that is because we start here, let's say initially I really don't have any choice, I just do a random guess. But after that, I know that it's been a tails. So I'm going to kind of more and more deterministically keep saying tails, 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 all the way up to here, right? And all the way up to here, my probability of tails, let's call this Q sub n over 3, is going to be basically 0, right? That's basically, I'm saying it's definitely a tails, not a heads. And then after this, I'm going to look at kind of what's going to happen in terms of how many such +1s I accumulate. And what you'll notice is that, okay, so up to here, I make 0 errors. So up to here, the first term in the regret is going to be 0, right? So you can divide it as sum t from 1 through n over 3 of indicator y hat t not equal to yt. And this guy is just going to be 0 all the way up to n over 3. But then after this, I'm going to start making probabilistic predictions, right? But the problem is I'm not going to change fast enough, because up to here it's been deterministically 0. And the way I'm changing is only at the rate of number of heads so far divided by total number of rounds, right? Which is going to be small, and it kind of the rate at which it changes is quite bad. So I'm not going to give you the exact proof sketch. But roughly what happens is on the remaining rounds, there is from t equal to n over 3 plus 1 up to n. So you have 2n over 3 more rounds. On all these rounds, if I look at in expectation over y hat t drawn from the strategy our friend mentioned, what's your name? Siddharth mentioned, we're going to have something of this form, right? Indicator that y hat t is not equal to -1, or sorry, is not equal to, yeah, -1. Right? That's our, +1. So that's our loss, right? But how fast does this grow? So this is basically what is the probability of heads, right? Or what's the probability of tails? Sorry, not heads. So that's going to be roughly something that looks like how many heads do I have so far? It's going to be t minus n over 3, right? Divided by t, something of this sort, right? And when you sum this up, what's going to happen is you're going to roughly accumulate you're going to have a summation that looks like a 1 over t summation, right? So roughly this guy, so if I look at expectation of sum t from 1 through n, indicator y hat t not equal to yt, the claim is that this is going to approximately look like log n-ish. something of this sort. Times n over 3. Okay? Something of this sort because you're accumulating factors of the form of 1 over t. Not necessarily. You can pick any non-half probability and then kind of just say, I'm going to kind of sort them. So any sorted order can completely will make it.
What sequence will give the highest regret if I'm following this strategy?
For this specific strategy?
At any time I look at the probability to pass, and that's based on that.
Based on that, what's the worst? I don't know what the worst one is. So that it would be interesting to work it out. I haven't done that. I think I was just looking for a strategy, and even the choice of 1 over 3 is just arbitrary. You could pick any p, and this is going to work like you take any, or basically take any disproportionate number of ones and minus ones and just sort them. They're going to fail. And they're going to fail roughly with this log n-ish factor there. I don't know whether that's the optimal thing or whether kind of the constants are optimal, but sorry?
It may have a crisp answer.
It might have a crisp answer. I haven't explored it. I guess I was looking for what's the optimal strategy. So this was more of just trying to kind of show a quick low bound. But we can look into that. It might be doable. It shouldn't be too hard. Yeah. Sorry? So that's like, it has a log n extra factor, right? Huh? Yeah. So this is from 1 through n. This is 1 to n over 3. This is n over 3 plus 1 to n. So I split it up into 2 parts.
Yeah,
oh, sorry. Yes. Sorry about that. Yeah. Thank you. Yeah. Okay. So essentially, small O of n regret is not possible even with kind of this strategy. So now, yep. Right. So when you say weighted, what do you mean? Right. So the strategy that was proposed was taking a weighted approach, meaning that we take recent data kind of more seriously than the past ones. Again, against this strategy, it might work. It's not very clear whether that's the right strategy in general. And I would, if our goal was exactly to minimize this regret, I'm going to claim that that is not going to be the optimal strategy. Because in some sense, if you look at our benchmark doesn't have any recency bias, right? So that's not going to be the optimal strategy. In fact, for this game, as I'll show you, there is an optimal strategy which we can work out, which is coerce result. And then kind of going from there, we have some answers for experts more than 2. So this is like a 2 experts problem. For more than 2, we have a little bit more knowledge. I'm not going to go into all of those details. But my guess is it's not going to be the optimal strategy. But there are kind of recency bias based approaches that do work in the sense that they'll get you up to constants of the right thing. And that those are in fact preferred from like an economics point of view. Because of the way data is really kind of occurs in market and so on. Okay, but let's not go into that. I'm kind of, because that's going away from what I was going for. I'm going to first flash the coerce result. Don't get alarmed by it. We'll go through it kind of slowly, but it was not written in directly the form that we are looking at, and it's way more general than kind of the exact problem that we're trying to solve. But what it says is the following. Give me any function phi that takes these n bits and maps it to the real, okay? And it has to have some property to it. The property is that if I take any one of these n bits and flip it from plus to minus, the function should not change by more than 1, okay? That's typically called the stability property, at least that's what it was referred to in the paper. So that's the stability property that we need. And what coerce result said was the following. My loss, which is the sum of my bit prediction losses, is upper bounded by this function phi of y1 through yn. This happens irrespective of how the adversary or whoever it is generates the y's. This happens, or there is a strategy that can kind of give this guarantee for all y's, if and only if in expectation over epsilons. So here epsilons are random coins, okay? So they're called Rademacher random variables. Each epsilon t is either +1 or -1 with probability half, right? So it's coin flip. If and only if in expectation over epsilons, this phi is larger than n over 2, okay? And he also, it's not there in the paper, but you can also draw the policy based off of the results. Okay, so again, this is a mouthful to read. So let me give you a plain English version of this. Plain English version of this is the following. For, again, I'm going to kind of leave out the caveat that phi needs to satisfy the stability condition. But the plain English version of this is that for any sequence or for any adversary, you can achieve the guarantee that your expected number of mistakes is smaller than phi of that sequence, if and only if you can achieve this guarantee against a random adversary who just flips coins. Okay. So this result, the first time I saw it, it was kind of mind-blowing for me. Because on the one hand, you're talking about something that's very game theoretic. You're saying the adversary is given any power, they can kind of go, kind of do whatever they want based off of how you're playing. And then this if and only if condition basically says that, can you get this guarantee in expectation over random coin flips, right? And the interesting part is that if you look at the strategy itself, it's not that while it is true that the random adversary is the min-max optimal strategy, the strategy that the player uses, which is this guy here, is not directly just kind of assuming that the opponent is just playing coin flips, right? But nonetheless, there is this kind of duality that says that if I'm able to achieve this kind of a regret guarantee, that my loss is smaller than phi, it's possible if and only if I can achieve it against a random adversary. Okay. Any questions or clarifications? Yeah. Versus random adversary. Okay, let's do that. It's part of the proof. So I'll do that in just a bit. Was same question? Okay. So the question was, why is it true that this second line here says that you can achieve it versus a random strategy, right? Let's think about it. Let's say that the adversary was playing, instead of Y's, the adversary was flipping coins and playing epsilon1 through epsilon n, right? What we are claiming here, right? Actually, let me just erase the board so I can. So what we are claiming out in the first, so let's go with the first direction, that is, oops, sorry. Let's go with the first direction, that is, if this is true, then the following here is true, right? So what we are claiming as what we are taking as our premise is that for all y1 through yn, the following is true. 1 through n, I'm going to put an expectation here, y hat t not equal to epsilon t is less than or equal to phi of epsilon1 through epsilon, right? And in fact, what we are saying is this is not just true for random draw of epsilons, this is true for every single draw of epsilon1 through epsilon n, right? So for every single sequence, I can give you this guarantee. So let's say that this is for some particular draw of epsilon1 through epsilon n, and now let's just, so here this expectation is over the algorithm, okay? Because remember that our algorithm is also randomized, this expectation is over the random algorithm. Now I'm going to take an expectation over epsilon1 through epsilon n, okay? So I'm going to essentially, so let me rewrite this guy as minus this is less than or equal to 0, right? So our premise was that this guy is less than or equal to 0 for every single choice of epsilon1 through epsilon n. Let's just slap the expectation over epsilons here. It should also still remain that it's less than or equal to 0. But now notice what this quantity here is, right? Y hat t's, what a y hat t is our strategy, and our strategy is only ever allowed to look into the past, right? It cannot look into the future. So which means that irrespective of how I play, I'm never going to be able to guess the next coin flip, right? Which means that my probability of getting this right is exactly half, right? And so in other words, this is n over 2, right? And then you're done, because now you have n over 2 minus expectation over epsilon phi of epsilon is less than or equal to 0. That's the trivial direction. That's kind of, so it's, I guess it's a mathematically more concise way of writing it down, but really all that it's saying is that we can achieve this, if we can achieve this bound, then it also holds true for random coin flips. But the interesting part is the other direction, right? If we can achieve this bound against random coin flips in expectation, then it holds for every single y1 through yn. And that part is also not too hard to see, okay? So the strategy that's used is qt is half plus half expectation over future epsilons. So epsilon t plus 1 to epsilon n of p y1 through t minus 1 minus 1 comma, oh, sorry, I forgot that it's going to be a,
then the Rademacher expectation is present for the by.
it's an if and only if. So it's yeah. Yes. Yeah. Right. So here what I've done is I've shown that A, which is, let's call this left-hand side A, I've shown that A implies B, right?
So there exists a Rademacher strategy. Pick the strategy that.
Yeah, I've picked the optimal strategy. I know that there exists a strategy. No, I haven't, so the randomized strategy that we are going to use is actually given by this guy here, right? But right now I'm just saying that assume that there exists a randomized strategy that for which A holds. If it holds for all sequences, it holds for all epsilons and taking expectation over epsilon, that's exactly the second part, right? What I'm doing now is doing the reverse direction. So for the reverse direction, I'm going to say that the probability that y hat t is equal to plus 1 is going to be given by qt, and qt is defined by half plus half expectation over epsilon t plus 1 through epsilon n. So for the future epsilons, p of y1 through t minus 1, comma minus 1, comma epsilon t plus 1 through n. Okay, minus of p y1 through t minus 1 plus 1, comma epsilon t plus 1 through n, epsilon n. Okay, so this is the strategy that we're going to use. So first, let me show you kind of how the proof works, and then I can give you a kind of a sense of how you derive such a QT. The idea is the following. Now, if I look at this guy, if I look at expectation, so okay, the way we are going to do this proof is the following. We're going to start from n, that's the very last round, and we're going to kind of, at the very last round, we're going to try to work out what's the optimal strategy and then work our way backwards. Okay, so if I look at Qn, this guy is, so let me actually directly look at expectation y over y hat t drawn from qt of indicator y hat t not, let's call this n, y hat n not equal to y, right? So I want to look at this guy. So the first thing you'll notice is that this is equal to, so if yn was plus 1, what is this guy? This guy is going to be 1 minus qn if, is it right? Yeah, if yn is equal to plus 1, right? If it is heads, then this is the probability of tails, and it's qn if yn is equal to a minus 1, okay? So if you gave me, if I kind of look at this quantity for yn equal to plus 1 and minus 1, it's 1 minus qn or qn. But the nice part is that if you work out expectation y hat n drawn from qn, indicator y hat n not equal to yn, and if I plug this strategy in, it's going to look like the following. It's going to be half, let me make sure I have the direction right. It's plus or minus. It's a minus. Good. So it's going to be half minus yn over 2 times phi y1 through n minus 1 comma minus 1 minus phi y1 through yn minus 1 comma plus 1. Okay. So you can work this out because it's either 1 minus this quantity, so you get a half minus of this guy whenever yn is plus 1, or if yn is minus 1, it's just qn, which is this guy, right, which is exactly what I wrote down here. So if I put my n equal to -1, you get that, right? Okay, so now the idea is the following. Yeah. 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 So the strategy is that I'm going to output a +1 with the probability QT, where QT is decided based off of the past draws. And it basically also, you'll need to be able to compute the expectation over the future epsilons and so on. Right? And at least as of this part, like if you can compute phi efficiently, if you can compute this phi efficiently, then it turns out that you can compute this strategy efficiently as well because of concentration properties of this guy. Okay, so now the idea is the following. If I look at expectation y hat n drawn from Qn, indicator y hat n not equal to yn, plus sorry, I should say minus phi of y1 through yn, right? So this is my loss in the last round minus phi. I can show that this guy is upper bounded by half minus expectation over epsilon n, phi of y1 up to yn minus 1, comma epsilon n, okay? Why is that? Because essentially, if I look at this guy here, right, with yn equal to +1 or -1, so you'll either get, so when yn is +1, you get 1 minus the difference divided by 2, right? But what you're adding there is phi of y1 through yn, right? So essentially, each time you cancel, so actually maybe let me just show how that works out. So if I did this in 2 steps, I would get the following. I would get essentially half plus, so this guy is exactly yn, half minus yn times expectation. Oh, there's no expectation for the last round. Phi of y1 up to yn minus 1, comma -1, minus phi of y1 up to yn minus 1, comma +1, right? And this is true for any yn. So I'm going to also add to this. Why am I subtracting? Okay, subtract to this phi of y1 up to yn, right? And now notice that if y1 was +1, I get a minus +1 minus of -1 over 2, right? And if yn is -1, I get the same thing. I get a -1 in this argument, and then I get basically -1 over 2 of this guy. Sorry, +1 over 2 of this guy, -1 over 2 of this guy. So for all y1, yn belonging to +-1, this is just equal to half plus phi of y1 up to yn minus 1, comma +1 plus comma -1. Divided by 2. Okay, and now I can just interpret this quantity as expectation over epsilon n, because the last guy is either +1 with probability half, -1 with probability half. So that's the final step of plus, sorry. Let me just make sure that there should be a minus here. Excellent. Okay. Yeah. Oh, the inequality comes because I have just been lazy. It's all equality. So everything here is equality. Sorry about that. Okay, so this basically tells us that you get this guy here. And now the idea for the rest of the proof is exactly the same. What you do is take this quantity here, right? And then add to it the expected loss at time n minus 1 and go all the way the same way. And what you'll end up getting if you did that is the following. So what you would end up getting is some t from 1 through n, expectation y hat t drawn from qt, indicator y hat t not equal to yt, minus of phi of y1 through yn. You'll just get that this whole quantity is exactly equal to expectation epsilon 1 through epsilon n. Oh, sorry, I'm missing a n over 2. N over 2 minus expectation epsilon 1 through epsilon n, phi of epsilon 1 through epsilon n. Okay. So what I haven't shown is repeating this argument from n minus 1 all the way down to 0. But if you did that, you're going to end up with the following, that each time I add one more loss, the sum of my losses minus phi is upper bounded by n minus the expected phi of epsilons. Okay. But our premise, which is the left-hand side, now remember that we are doing B implies A. B tells us that this quantity is negative, right? And so from B, you get that this is less than or equal to 0. Okay. So what we have just shown is that this guy here implies that for any sequence you can get this result. Okay. Questions? Huh? Yes, good question. I actually have, sorry, what happened here? So give me 1 second. So I actually had that as a question for you guys. Right, so where did I use the fact that phi is stable? The fact that phi only is allowed to change by 1 on any coordinate. Sorry?
Make sure QT is.
Yes, so to make sure that QT is between 0 and 1, right? Because QT is the probability of plus 1 or minus 1. And it turns out that this is one big caveat in coerce result. It kind of hinders its use for arbitrary fees. You need the stability condition, and that can be kind of a problem, right? So again, I didn't tell you, I just kind of showed you what QT was. I directly kind of showed you the result. It turns out that it's not too hard to actually derive QT. The way it's done is, again, you do the same thing. You start from n, go all the way to 0, right? So when you start at n, you can think of it as a one-step kind of, if I had to play the best Qn, and if the adversary played the worst Yn, what would happen? And that's a simple saddle point optimization problem, and it has a closed form solution. That's where I got the QT from. Okay, we'll see another version of this where it'll become a lot more clearer. Okay. All right. So now if we go back to our problem, the bit prediction problem where I just want to do as well as the majority, what does this give us? So the nice part is coerce result kind of tells us, I mean, it's an exact result. So it also tells us kind of what's the best I can hope for, right? So if this was my notion of regret, I can say, how large should this quantity on the right-hand side be, right? C sub n. So let's call that C sub n. So I want to just say that phi is going to be this guy, which is my comparator, plus some C sub n. And we already know that C sub n is required, right? Because I already argued that even if you had the best strategy that you could possibly come up with, against a random adversary, this roughly looks like square root n over 2, right? Because that's what a random adversary, if the adversary was random, what I know is that whatever my losses is always going to be n over 2, and this guy is going to have a deviation of at most square root n over 2, right? Around n over 2. And so I know that this quantity Cn has to be at least root n. And the interesting part is you get pretty much exactly the right answer. So if I worked out Cn from coerce result, right, how do I do that? I want to essentially ensure that expectation over epsilon 1 through epsilon n of phi is lower bounded by n over 2, right? So I can work out Cn by just using this equation. So Cn is just n over 2 minus the expected this quantity here, okay? And then from here, it's simple enough math. You can write down any indicator in the linear form. So it's 1 minus b times y divided by 2, when b and y are binary variables. Okay, and then finally, okay, so is this part clear for everyone? I can go over it if you want me to go over it. It should be fine. Okay, great. So you get square root n over 2. Now the interesting part and kind of where this relates to more traditional learning theory is that it already gives us a glimpse of kind of one of the more sophisticated tools in learning theory. So I could ask the same question where I'm not just saying I want to do as well as the majority. Imagine the following scenario. I basically say I have some collection of sequences plus 1 minus 1 up to n, right? And I'm not going to I'm not asking that I do, so what I'm going to ask is I want to ensure that my total loss when I'm doing this prediction problem does as well as the best in the collection. And again, it's very important to remember that when I say best in the collection, I mean that it's in hindsight, meaning that I get to see y1 through yn, then I pick the best f in script f, right? So majority is just the simple example where there's just there are 2 points in script f. So majority is the case where script f just consists of 2 things, which are all plus ones and all minus ones, right? It's just 2 of these guys. But more generally, you can have an arbitrary collection script f of plus minus 1 up to n. And now what you can very easily verify is that phi does satisfy this condition that if you flip 1 coin or if you flip 1 bit, it changes by at most 1, right? Because you're essentially comparing this guy versus the same guy. If one of the bits is flipped, it can at most change by 1. Okay, it's simple enough maths. I'm going to leave it out. And if you followed the same steps that I showed you in the previous slide, except that instead of b, you call it f, which is now a vector of f1 through fn, then what you get is this quantity here. So such result, that is a regret for this guy. If I want the best upper bound for the regret of the following form for any arbitrary f, script f, which is a plus minus 1 to the n subset, it's achievable if and only if, or in other words, the best possible bound that's achievable is this quantity here, which is half expectation over epsilons, max over f in script f, ft times epsilon t, okay? And this quantity here is known in learning theory as Rademacher complexity, and it kind of forms like the heart of VC theory and kind of a lot of the bread and butter of kind of standard learning theory. And the interesting part is here, you get this so typically when we talk about learning theory, we think about there's a fixed distribution and your x's and y's are drawn from this fixed distribution, and you're interested in kind of your future losses when x's and y's are drawn from the same distribution, right? Here we are basically saying, so there are no x's here. I've kind of made that part easier, but let the y's kind of come even arbitrarily. And what it says is that the right geometry here is this Rademacher complexity here. And to give you a sense of what Rademacher complexity is doing, it's saying how well does the worst f in script f correlate with random noise, right? Because for every draw of epsilon 1 through epsilon t, you're basically saying, let me take a random draw of epsilon 1 through epsilon t. So it's like saying for each of the n points, I'm giving a random plus minus 1 label. How well does my best model in script f correlate with this guy? If it correlates highly, it means that the model is really complex. So you'd expect that you don't get good rates. And that's exactly what's seen here. And a crude upper bound that one could get is something of the form of square root n times log cardinality of f. Okay, but there are more refined upper bounds that one can get as well. Okay. So the idea here is that your regret is compared with some class of model script f, and it's going to be the Rademacher complexity of that model script f. Right? So in some sense, you can think about script f as what's given to you. Okay? And in fact, the same exact result can be extended. Okay, the same exact result can also be extended to the case where you actually do have what's called context, right? So typically when I think about learning, it's not that you're just predicting bits. Typically you're given an image, some image, and you're going to ask whether you're asked example, whether it's a cat or a dog, right? So you're given x's and you're predicting y's here. And what we can kind of conclude from this result fairly easily is if I were given x1 through xn in advance, then you can apply this result as is. Because what I can do is I can define my class script f as f projected on x1 through xn, right? Take every f in script f. Here, script f is a function that takes me from the instance space to a plus minus 1 space, or more generally, some real space. And essentially what I'm saying here is that if I took all the f in script f, and if I project the script f onto x1 through xn, that forms a class of vectors in plus minus 1 to the n, right? So if I look at script f, I'm sorry, I'm overloading notation here, so maybe I should do the following. On x1 through xn is defined as f of x1 up to f of xn, such that f is in script f. So for every f in script f, I get a vector fx1 up to fxn. And if I look at this set of vectors, and I can essentially apply coerce result as I showed in the previous slide to that. More interestingly, what you can also do is you can imagine I gave you access to unlabeled data, right? So I tell you that x1 up to xn or whatever the x's are drawn from a fixed distribution, and I gave you access to this unlabeled data, or I give you access to draws of x's from this distribution. Then it turns out that you can essentially come up with the same strategy and the same Rademacher upper bound by kind of padding up your strategy where it has x1 up to xt minus 1 for the past x's. This should have been xt, sorry. This should have been xt, not x prime t. So you go all the way up to the current time where you're given x1 up to xt. And then for the future, you're going to kind of draw x prime t plus 1 up to x prime n from this fixed distribution. Okay? All right. All right, so now the next question that we are interested in is what if, sorry? So, okay, so the question was computing these QNs, are these straightforward? So think about what computation of QT in general for a phi is, right? It's going to be half plus half times expectation over epsilon of the difference of the phis with futures pushed with epsilon 1 to epsilon n. Now, if you're able to compute this expectation directly, then you're done, right? Typically, I don't expect that you'll be able to compute these epsilons directly, but the nice thing is the same stability property that I mentioned, where kind of things change by at most 1, also guarantees concentration inequality. So if you look at kind of standard concentration results, there is this famous result called McDermott's result, McDermott's inequality, which basically says that any function phi that changes by on any coordinate by at most 1, it has the concentration property that if I take y1 through yn random, expected phi of that value is close to any, I mean, on average over, if I take a random draw of epsilons, phi of epsilon 1 through epsilon n is close to expected phi of epsilons up to like order root n. And we are allowed to kind of have that. So that means that all I need to do for this guy is on every round, I draw future epsilon 1 through epsilon t plus 1 up to epsilon n randomly once, and I compute this quantity, and that works in expectation. And it also works in high probability. So as long as phi is efficiently computable, this is efficiently computable. What that means for us is if you come back to kind of like the scriptf version here, it means that if I can solve the ERM problem efficiently, meaning that if I can minimize my loss with respect to the model class efficiently, then this problem is solvable. Yes, absolutely. So yes, so that's not for today's lecture, but yes, I'll kind of mention how, what would you do kind of stepping out beyond kind of the simple bit prediction scenario, and more generally, in general, it's very hard to compute things exactly. So we'll start moving away from how do you compute phi or the strategies exactly, and kind of how do you come up with relaxations and so on. So Cover, he was just interested in the bit prediction problem, and that's about it. Like his paper is like, it's sweet and simple and just kind of just a few pages long, and it's literally just that. So it was I don't think it was necessarily connected to ML because it's 65, right? I don't know, at least as far as I have seen out there references, I don't think he was even aware of, or it's not very clear whether he was kind of in the same group or whether thinking about Shannon and like the mind reading machine, etc. Yes. Right. I mean, yeah. So I think kind of like the interesting part of the result was just that it works for random epsilons. It works. I mean, it works for random outcomes. It works for every single sequence. And I think kind of this was back when kind of I think he was thinking about more of from the statistical angle, with kind of whether you have, I mean, you have random generated instances or whether it's like whether you have like saying kind of like you're looking at some kind of treatment effect kind of things where Y's could vary. But his paper itself is like just plain math. So it's like I'm not, at least as far as I can tell, I was not able to tease out kind of what was the modern motivation for it. Yeah. Okay, great question. So for those of you, so what's your name? Nishant? Nishant basically asked, what if I run Hedge? Hedge is an algorithm for online learning. It turns out that if you run algorithm for Hedge, not just for the +1 -1, you can also run it with scriptf, right? Then you will get kind of the style of bounds that you get here. So, okay, it turns out that this algorithm is the min-max algorithm. Hedge is not min-max optimal. It's kind of, it has like constants off, right? This algorithm is the min-max algorithm. Now, in terms of kind of how it behaves with respect to Hedge, Hedge kind of, I mean, in some sense, Hedge always smooths out, right? Because Hedge, basically what Hedge does is it kind of does the Boltzmann kind of distribution roughly, right? If you think about it, of number, like where you put number of heads up there. And so that always kind of smooths out. This one is trying to be min-max optimal. So it has like more peculiar behaviors based off of kind of this expected value. Now, of course, kind of the bug doesn't stop there in that like we are not just interested in, in coerce result as such, but the reason why I like coerce result is unlike if you think about Hedge or kind of like the earlier kind of like where things like online gradient descent, how they were kind of developed like on a kind of case-by-case basis, right? But coerce result kind of worked with kind of the base problem in mind. You kind of work from the foundation. So this is the exact problem you want to solve, and then you kind of derive an algorithm in a sense. And that's the aspect that we are trying to kind of emulate. At least if you look at the history of Hedge, it was not like Hedge was the first thing they came up with, even though up to constant, it's the right algorithm in terms of its bounds. So in some sense, it was more like kind of cleverly trying out things. So it required a little bit of genius. Here, I think once we make it into a recipe, the idea is that we don't really need kind of people like, I guess, like Manfred or Wolf and these guys to kind of come up with algorithms. Maybe it can just kind of come out of the framework. Okay, so the next question that we are interested in is if we want to kind of have, so right now where even the result that I showed you where you have a, actually what's the time? Oh, okay. Huh? Sorry? 12:20. Oh, this is just the time, right? Okay, cool. Cool. All right. So if you look at the result that I showed you with the scriptf, it was great. It was fairly general, where we were able to kind of say we get a result of this form here. But if you notice, I'm setting these scriptf to be like ±1 to the n in advance, right? So if imagine kind of I wanted my machine to do kind of have a small regret compared to Shannon's machine or something like that. Now, what Shannon's machine itself was doing, the comparator there was basically looking at what y1 through yt-1 were, and it was kind of predicting the next bit, right? So if I want strategies that can compete against scriptf that can take into account past knowledge, that's going to require a little bit more work, okay? And so the question that I wanted to ask is, what if we had context-dependent past? Okay, so context is a way to kind of, in typical learning theory, you kind of think about input instance xt, and in online learning, typically these input instances are called context. The simplest version of it is xt could just be y1 up to yt-1, right? xt just kind of encodes y1 up to yt-1. And what if we wanted to kind of have a similar result that also kind of uses context from the past? Okay, what do you think would be kind of stopping us there? What would be like there are a couple of problems, but what would be the first one that kind of blocks us there? Any guesses? So the result that I showed you is independent of the past or the benchmark is independent of the past. It's like fixed. But if you were to try to emulate the same method, what do you think would fail? So this one is a subtler question. So if you kind of look at what phi I would need, right, your f's here would depend on the past, right? And one big problem that comes out from this is that if f's depend on the past, then very quickly the stability condition I was talking of is going to break fairly badly. Because what could happen is that if, let's say on round one, I played a heads versus a tail, from then on, kind of the two strategies in scriptf could vary quite a bit, right? So very quickly, the stability can kind of fall apart, right? In this version here, it doesn't fall apart, where I just have kind of what I'm comparing with is just like a single f in scriptf. But if this f's are dependent on the past, this can break quite badly, okay? So one thing that's easy for us to do when you have a problem of this form is to basically completely avoid that problem and change the problem setting to make life easier for you. So let's start with that. Okay, so we're going to make the problem easier on us. And what I'm going to do is I'm going to look at what's called the linear betting game. Okay, so the earlier version that I was thinking about was essentially, you can think of it as a prediction game where I'm trying to predict if the next bit is +1 or -1, but that was about it, right? Here, I'm going to do a little bit more. I'm going to put kind of my money into the algorithm. So the way we're going to think about the game is the following. So the learner, so again, it's going to be a simple bit prediction kind of problem, except that this time I'm going to kind of think of it as a betting problem. So specifically, imagine that I have the following. On every round, the learner has to place a bet. So every round, two teams play, team A and team B. Okay, on every round, there could be two different teams, but I'm just going to call kind of the left one as team A and right one as team B. And the learner has to place some amount of bet. We'll represent that amount of bet by the magnitude of y hat t. And it has to place its bet on either team A or team B. So I'm going to use the sign of y hat t to denote whether it's going to be on the team A or team B. Okay. Or in other words, I can just think about y hat t as both my bet and who I'm placing the bet on. Right? Both the bet amount and whom I'm placing the bet on. How is that? So I just look at sign of y hat t. If it is plus, it's team A. If it is minus, it's team B. And if I look at the magnitude, that's the amount that I'm going to bet. Okay. And after I place this bet, the result of the match is revealed to me, right? So it's basically, I know whether team A won or team B won. And the loss that I suffered is basically how much money I lose, right? So if y hat t was positive and yt was also positive, right? Then my loss is negative, meaning that I gain money. Okay, so as a learning theorist, I like to kind of think about things in terms of losses. You can also think in terms of rewards where you just flip the sign. So the idea is that if my bet was right, then I gain money, so my loss is negative. If my bet was wrong, then this is going to have a negative sign. Y hat t times yt is a negative sign. So minus of that is positive, which means that I have a positive loss, right? And how much do I lose? It's exactly the amount that I bet, right? So that's the game that we are interested in. And our goal again is that we have some function phi that tells me if, that takes me from the ±1 to the n to the reals. And I want to ask, when is it possible that the total amount that I lost is upper bounded by this benchmark phi of y1 through yn? Okay, that's the goal that we are interested in. And the nice thing here is that now that I've kind of not written it down with the indicators here, it removes this necessity for us to have these phis to be have the stability property, right? Where I flip one index of phi and things cannot change by more than one. So I don't really need that. And so the result that you can get is the following. For absolutely any phi out there, you can get that there exists a strategy with the guarantee that my expected losses is upper bounded by phi of y1 through yn, if and only if expected phi under epsilon1 through epsilon n is greater than or equal to 0. Okay, it's again the same thing. It's saying if I have a betting strategy that works against random outcomes of games, then or in other words, if basically for random outcome of games, I can essentially get this following result, which is that there is a strategy that works, then there's a strategy that works for every single outcome out there. Okay, and the proof is also fairly similar. So since I have 5 more minutes, oh, okay, cool. So, I'm so sorry. It's my bad. It shouldn't be an indicator. It should be, it should be the loss. I clearly have cut and paste. Let's see, do I have the, so, okay. So let me just write it out here. So the result says the lemma should be the following. For all phi that maps from ±1 to the n to the reals, the following is true. There exists strategy such that against any adversary, in a sense, so I wouldn't call it certain because it's not a probability, right? It's the magnitude of bet. So so that's why I want to call it the betting game. Think of it as you have, I mean, you have enough money to bet on each day. And then, so you can, so I'm not putting any restriction on how large your bet is. You can basically choose a team and you can put all your money on that. If you lose that money. If you gain, you basically gain exactly the amount that you bet. That's it. So I don't want to conflate it with probability because that's where things start getting any real value, yes. It's from phi, the phi is the benchmark, right? It's saying if I had some function of the outcomes of the game, does it compete with that? And what you'll also notice is that, yes, as I mentioned it, I said y hat, and there's no restriction on y hat t as to how large the magnitude is. But if you look at the strategy, you will kind of realize that it has something to do with phi. And so there is like, you can kind of write down like some kind of coarse upper bound. It's just that it need not be very strict as in the prediction game. So essentially the idea is that there exists a strategy against any adversary that guarantees that the sum of my losses is upper bounded by phi of y1 through yn, if and only if expectation over epsilon 1 through epsilon n, p of epsilon 1 through epsilon n is greater than or equal to 0. Okay. And again, as I mentioned, one direction is trivial. Imagine that the y's were just random coin flips. Then y hat t can never predict random coin flips. So in expectation over epsilon, this guy is just going to be 0 on every round, right? Because essentially, I don't know whether I'm going to win or lose. Probability half I win, probability half I lose. So in expectation, each round I gain 0. But on the other hand, the right-hand side is going to be, so the idea is that for all epsilon 1 through epsilon n, if A, let's call this one A, and this one B, right? So if A is true, then using that strategy, I get that sum p from 1 through n minus y hat t times epsilon t is less than or equal to p of epsilon 1 through epsilon n. And so putting expectation over epsilon 1 through epsilon n, I just get that sum p 1 through n y hat t times epsilon t is less than or equal to expectation over epsilon p of epsilon, right? And this guy is 0, so that's that one. The other direction is kind of also similar in that the strategy that we are going to use is the following here, right? So let me, it's almost a replica of the previous one, except that you just don't need the condition, okay? So, and the nice thing about this is because we are in this betting game and the loss is linear, you actually don't need randomization this time. Earlier, I kind of made this point in the bit prediction problem that if without randomization, things are not going to work. But now, because you can put in any amount of money towards kind of which team is winning, you can kind of, you get a softer prediction in a sense, right? So you don't need the randomization. So the other direction is the following. If I look at y hat n minus y hat n times yn, right? So this guy, let's say minus phi of y1 through yn. This guy is equal to what? If I plug this in for the last guy, it's phi of y1 up to yn minus 1, comma minus 1. Sorry? Good point. Did I leave it out? Yes. Thank you. Yes. Okay. Great. So y hat t has to have a half. Expectation epsilon t plus 1 through epsilon n of phi of y1 up to yt minus 1 minus 1 epsilon t plus 1 up to epsilon n minus phi y1 up to yt minus 1 plus 1 epsilon t plus 1 up to epsilon n. Okay. So there is a half that should be multiplied here. I missed that out. So if I did that, I would get half of this guy, y1 up to yn minus 1, comma plus 1. Okay, and I get that minus of p of y1 up to yn, right? Wait, am I? And oh, there's a yn times this guy, right? Y hat n. So it's going to be yn divided by 2 times this guy. And now the strategy is again the same. If this was a plus 1, then I have a half times minus 1, and then I have a plus half times plus 1 minus half times 1, right? So again, it's the same idea that for all yn, so for all yn, you get the same guy that y minus y hat n times yn minus phi of y1 through yn is equal to phi of y1 through yn minus 1, comma minus 1. Oh, great. Okay, perfect. Although I did erase it, so I'm just going to, there's a half here, plus phi of y1 up to yn minus 1, comma plus 1. Right, and that's exactly expectation over epsilon n, and that's this guy. Okay. And now the idea is that the half that was carrying over is not there, but other than that is the same idea. Now kind of plug this into n minus 1 and go all the way to 0, you get the result, right? And the nice thing now is you don't really have the condition on phi. Okay, so I guess with that I should let you guys go get lunch. But before I do that, I just want you guys, so forget about the math that's written here. Here's the thing to kind of think about during your lunch. And I guess before the next time I talk to you guys, think about this betting game where I tell you, let's say we are talking about a soccer match. There are m players and you're going to play for n rounds. And I even tell you which are the pairs of teams that are going to play over these n rounds. So I tell you kind of it's going to be team 1 versus team 20, team 22 versus team 13, and so on, all the way up to these n. I give you these pairs in advance. And now what you want to do is you want to do as well as the following benchmark. Okay, the benchmark is the following. I basically give a score for every team. Team 1 up to team m have some score. I'm going to call it w1 through wm. And if team I plays against team j, the amount that I'm going to bet is the magnitude of wi minus wj, and I'm going to bet it on the team that has the higher score. Okay. Now, if this was the game, can you kind of use this lemma that I mentioned to kind of come up with a strategy, and what would it look like? Like if I were to ask you to kind of come up with kind of a quantity on this regret, which is exactly the regret that I mentioned earlier, which is compared my losses compared to the loss of the best strategy that just puts a score for each of the teams and then bets according to the difference in scores. How large should this quantity be in terms of n, in terms of m? Okay. So I'll let you guys think about it. Thanks, and I'll meet you guys later.